In this lesson, we're going to start to talk about series that have variables in them, and particularly then we'll need to look at establishing intervals of convergence for those types of series. Before we start looking at those series, particularly we'll be looking at the Maclaurin series. Let me think for just a second about what we've been talking about, what we've been looking at, right? So we've been doing, say the summation as k goes from 1 to infinity of 1 over k, or the summation as k goes from 1 to infinity, say 1 over k squared, right? And then we talk about whether that series converges or diverges, all right? Now what we want to do is say, okay, what about a series like this? The summation as k goes from 1 to infinity of 2 minus x to the k. Okay, where x now is a variable. Okay, so this, if we started expanding this would be something like, right, let's do a k minus 1 just so we can do minus 2 minus x to the 0 plus 2 minus x to the first plus 2 minus x cubed plus, I'm just going to put my dot 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 there, okay, cubed, squared, there we go. So you can see now that this is going to, right, if we were to expand this, that's a polynomial, okay? And so now we're going to be able to say something like a function in x, f of x, that we may be familiar with can be approximated by or is nearly equal to the summation as k goes from 1 to, and I'm going to put n up here because for the most part what we're really going to look at is finite term approximations, although we'll be able to find one that's an infinite. But let's just think about, you know, in terms, right? And we might do something like, and I'm just going to put some numbers in here. 2 times x minus, actually let's do, yeah, well this will do a good one. Let's do 2 over k factorial times 2 minus x. How about x minus 2? Just do this. To the k, minus 1. All right, so now we have a function, right? And we could take, you know, we could take the actual function would then be the limit as n goes to infinity. The summation as k goes from 1 to n, 2 over k, x minus 2 to the k minus 1. Now, I just made these up to try to give us a feel for what kinds of operations we're going to be doing. So we're going to need to talk about a lot of different things in order to do this, but this is the general idea now. We've been developing these series, but where we've really been going is this idea. And the general way that we would say that idea, I try to use specific numbers. I think sometimes that's easier for you to see. That f of x is nearly equal to the summation as k goes from 1 to infinity of a sub k, x minus x naught to the k. Let's do a minus k. We'll do a power series, right? So we're looking at developing terminology and mathematical rigor to taking a given function and finding a series approximation for the function. That's really what we're going to try to do. Okay, so we're going to have to build up a bunch of stuff to that, but in the back of your mind, you probably want to think about that. Okay, so the first thing, right, so here's our power series. So hopefully you got a feel now for what we're doing. We're going to build this series. We're going to build this series around some value x naught. Okay, so in this, I'm getting right now. Variable in this problem is going to be an x, right? The a sub k's or the a sub n's are constant. But they might change. You know, those are constant values, but they might be different in each term. We want to find the interval of convergence. That is, we want to find values of x for which this thing converges, okay? And what we'll do for the power series version of this, we'll look at absolute convergence. So for what values of x does this converge? We'll talk about that, how to test that in a minute. To find those values, we're going to use the root test or the ratio test, and then we'll get our test statistic rho, and then we'll be able to say, well, it converges for rho values of whatever known to the test, typically less than 1, right? And then we'll be able to say for x naught, for values of x between this interval, you have rho convergence rows, all right? And we have a similar process for if we use a minus k there. So what we've got now is some series ideas, and we need to find these intervals of convergence. So that's the first thing I want to do, or the first thing that we're going to do is look at finding the interval of convergence. It will turn out to be that for lots of well-known functions that we're used to working with, the interval convergence will just be it will be all points between minus infinity and positive infinity, which is really nice. Okay. So let's find the intervals of convergence. So here we got x plus 1 to the k over k. All right. So what we're going to do is we're going to use the ratio test here. All right. So I'm going to let rho be equal to the absolute value of a to the n plus 1 over a to the n. I can leave my limit in there, sorry. Limit as n goes to infinity, there we go, a to the n plus 1 over a to the n. So that's what we're going to do, so let's come down here and sort of plug in our terms here. That'll be the absolute value. A to the n plus 1 is going to be x plus 1 to the k plus 1 over k plus 1. Let's see, we got to do this for n. Over x plus 1 to the n over n. All right? So let's see, let's simplify that a little bit. I'll flip the denominator and just click that up, so that'll be x plus 1 to the n plus 1 times n over n plus 1 times x plus 1 to the n. Let's see, so I can slide out some terms there, and that'll be limit as n goes to infinity of n over n plus 1, right? And that's all positive, so I don't have to worry about that. I'll slide that, it's not going to change the signs. And then I'm going to be left with x plus 1 to the n plus 1 over x plus 1 to the n. And that's going to be the limit as n goes to infinity of what, that'll be x to the n plus 1 is x to the n, x plus 1 to the n times x plus 1, and then those cancel, and I'm left with the absolute value of x plus 1. All right. So now what we know is That's the rho is equal to the absolute value of x plus 1. So I'm going to come over here and say rho equals the absolute value of x plus 1. Recall that the the ratio test says that the series converges for rho less than 1. So we're going to say the absolute value of x plus 1 is less than 1, and if I do that, I'm going to get what? Minus 1 is less than x plus 1 is less than 1. Add 1 around, that gets me, subtract 1, that's going to give me minus 2 is less than x is less than 0. And series converges for the interval from minus 2 to 0. Now, when rho is equal to 1, the test fails, which means we don't really know, right? And rho equals 1 gives me the absolute value of x plus 1 is equal to 1, which gives me x equals minus 2 or 0, right? So we need to check those points. Since the test failed, so when x is equal to minus 2, right, what do we have? I'm going to have to go back up here, and we're going to have the summation as k goes from 1 to infinity of x plus 1 to the k over x, and we're going to do this at x is equal to minus 2, so that's minus 1 to the k over k. Oh, forgot my summation. So we get the alternating harmonic series, which we showed earlier is a convergent series. At x equals 1, the summation from k goes from 1 to infinity of x plus 1 to the k over k. That gives me what? The summation as k goes from 1 to infinity of 1 plus 1. That's 2 to the k over k. No, not equals, at x equals 0, I'm sorry. That gives me 0 plus 1, that's 1 to the k over k, and that's going to be what? The summation as k goes from 1. 1 to the k is always k, that's 1 over k. This is the harmonic series. So diverges at x is equal to 0. So a little more space here. Therefore, the interval of convergence includes minus 2 and is not 0. Okay? And everywhere else, right, when rho is larger than 1, the ratio test diverges by the ratio test diverges. So this is the interval of convergence. Let's try one more. All right, so we're going to do the ratio test again. So rho equals the limit as n goes to infinity of a to the n plus 1 over a to the n. And for this, that's going to be the limit as n goes to infinity of, let's see, a to the n plus 1 is going to be n plus 1 over 2x to the n plus 1 over n over 2x to the n. It's the limit as n goes to infinity, or flip those around, that's going to be the absolute value of n plus 1 times 2x to the n over 2x to the n plus 1 times n. It's going to be the limit as n goes to infinity of n plus 1 over n divided by 2x to the n, 2x to the n plus 1. Limit as n goes to infinity, let's see, that's going to be n plus 1 over n times the absolute value, the 2x to the n, and the numerator will cancel the 2x to the n in the denominator, and you'll be left with 1 over 2x. As n goes to infinity, n plus 1 over n goes to 1. So this is 1 over the absolute value of 2x. And that's rho. So now we want to do our convergence testing, right? So rho less than 1 gives me 1 over 2. The absolute value of 2x is less than 1. That's 1/2 times the absolute value of x is less than 1. Multiply through by a constant 2. That's going to give you 1 over x is less than 2, which you invert that, that gives you the absolute value of x is greater than 1/2, which gives me that other an open in two intervals. So greater than absolute value of x greater than absolute value of x greater than 1/2 is from minus infinity up to minus 1/2 union with 1/2 up to infinity. That's my initial interval of convergence. Now we need to test rho is equal to 1. That's the minus 1/2 and the 1/2. See if it converges on those intervals, because those are cases where rho is equal to 1 and the test is inconclusive. K over 2x to the k. That's going to be the summation. So when x is equal to minus 1/2, that's going to give me the summation. This k goes from 1 to infinity of k over minus 1 to the k. All right. So that's going to be equal to, let's see, that'll be minus 1, that'll be minus 1 plus 2 minus 3 plus 4 minus 5 plus dot dot dot. So that series diverges. by the nth term test. Write the nth term test. The limit as n goes to infinity of minus 1 to the n is equal to, this alternates between two, you have this alternating piece. So that's going to be essentially plus or minus infinity, since we don't have a, so diverges. All right, so the minus 2 is not included. Let's see what happens with x is equal to 1/2. So the summation as k goes from 1 to infinity of k over 2x to the k at x is equal to 1/2. That's going to give me the summation as k goes from 1 to infinity of k over 1 to the k, which is what? Summation as k goes from 1 to infinity of k, and that series diverges. Same test. Limit as n goes to infinity of n equals infinity, therefore diverges by the nth term test. All right, so the interval of convergence minus infinity up to minus 1/2 union 1/2 to positive infinity. All right, and it diverges everywhere else. All right, so now we have this idea of being able to establish the interval of convergence for a given series that includes the variable x.